Learn something new every day for everyone. Have something you want to learn? Submit yours at lumolab.org.
Over the next 30 episodes, we are deconstructing the papers that built the AI revolution. We are organizing this journey around one mind, Ilya Sutskever. Why him? Because from AlexNet to GPT, from sequence models to scaling laws, he didn't just witness the revolution, he architected it. But before we look at the specific machines, we need the blueprint. We need to answer a fundamental question. What is learning actually doing?
The answer is the unifying theme of this series. Learning is compression. When a neural network classifies an image or predicts the next token, it isn't memorizing data. It is finding a description that is more compact than the raw input. Think about it. If I show you 1 million images of cats and dogs, you don't store a million JPEGs in your brain. That's terabytes of data. It would be impossible. Instead, you develop a mental model.
You distill those millions of pixels down to a few kilobytes of features, pointy ears, whiskers, snout shape. You've compressed the dataset. This distinction between memorizing the pixels and learning the rule is the difference between a database and intelligence. If you memorize, you can only recall what you've seen. If you compress, you understand the pattern. That allows you to predict data you have never seen. That is generalization. But you can't just compress everything. Random noise has a file size floor you cannot break. Successful learning requires 3 pillars. The first is inductive bias. This is the structure we build into the model to limit what it looks for. Take a convolutional neural network. It enforces translation invariance, meaning a cat at pixel 00 is the same as a cat at pixel 200. By restricting the search space to these specific symmetries, we make compression mathematically possible.
The second pillar is optimization. We need an algorithm, like stochastic gradient descent, that can navigate the high-dimensional loss landscape to actually find that compact description. And the third pillar is data. Without enough examples, there is nothing to compress. But be careful. Feed the model too much noise, and it will waste its limited parameters compressing static instead of signal.
This compression thesis isn't just philosophy. It explains the engineering techniques we use every day. Consider regularization, like dropout or weight decay. Why do we intentionally damage our networks during training? Because by limiting the information capacity, we force the model to stop memorizing noise. If the model can't remember every pixel because we keep deleting its neurons, it has no choice but to learn the rule. This framework also explains scaling laws, why larger models work better. They simply have the capacity to capture more complex compressions. As we move through the next 30 episodes, keep this lens in mind. In Episode 1, we'll see how AlexNet used depth to hierarchically compress visual features. In Episode 9, we'll see how the transformer used attention matrices to compress sequential dependencies more effectively than recurrence.
We will eventually reach the deep theory in Episodes 19 through 24, minimum description length and Kolmogorov complexity, where we prove mathematically that compression is fundamental to intelligence. The story of AI, from neural networks are a failed idea to the most important technology humanity has ever built, is really just the story of learning to compress better and better. Let's begin.
Thanks for watching, and keep learning.